Hi guys, today we're going to be looking at exponential functions. So we're continuing on our journey into the work that we've done on logarithms. So we looked at logarithms, and I did say at the time that we were going to come back and we were going to look at the work that we did, or we started to do, on exponential functions, and more specifically the work that we did, or the work that we considered, on what we now, or what I'm going to call, Euler's number. Leonhard Euler, a Swiss mathematician, come up with this number, this number with a base e, that I did say at the time we were skimming over, but it's hugely important in mathematics, and there was some of the work that we wanted to do first on logarithms, so that I could give you a better introduction and a better feel for why we consider it so useful in mathematics. So let's just take our time on this and go back and let's have a look at exponential functions. And when I'm talking about exponential functions, what I'm actually talking about is functions of this form, a to the x. So we're talking about things like 2 to the x, 5 to the x, anything like that. So these are the sort of functions we're talking about, where the argument, or the unknown, the x that we're solving for, is an exponent in our equation, or another way of an exponent is a power. We often, when we look at bid mass, it's sometimes given as bed mass, where E stands for the exponent or the power. Sometimes the I, when we use bid mass, is for indices, so it has a few different words that we use. So here, anything of this form, the base can be anything. When we talked about logarithms, if you remember, we had 3 buttons on our calculator that were important to us. The first one is this log, and then it has a square there and a square there. And we can now put in any base that we want in there and any answer in here, and we can get the value of that logarithm. Remember, these logarithms are just numbers that we're working with. They look different, they're given in a different way. So we talked about something like this, where we said log with a base 2, 8, and we looked at the alternate way of writing this in this exponential form, this exponent form, where we said x is equal to the logarithm or the power, so I put a power in, that when I give it a base 2 gives me the answer 8. And what we said is that clearly, if we look at this equation, then x must be equal to 3, because 2 cubed is 8. And so this, if you put it in a calculator, log 2(8) is just a number. It's the number 3. It looks different. It's almost like a number in disguise. But here, the value of this particular logarithm is 3. So we've got this log square square button that we use. And then there's 2 other buttons on our calculator. We have this button here that just says log. Now this is log base 10. And you can imagine in things like engineering, or when we change from imperial, from metric to imperial, everything that we're working with now is on base 10. I mean, we could, and there is talk around this, that we've got 10 fingers on our hands, and it makes it easier to work in base 10. Not everything that we have around us is base 10. For example, if you think about time there, we're looking at hours, minutes, seconds, and we've got base 60 that we're working around. But a lot of our calculations now, if we're thinking about going between different units of length, you're going to be multiplying by 10, 100 or 1000. So 10, 10 squared, 10 cubed. All the numbers that we work on, we work with base 10. So this log button there, when it hasn't got any base written down there, just means log base 10. So we've got these 2 buttons. This one is a fairly new addition to our calculator, and to me it takes a little bit of the fun out of it because we don't have the change of base, or we don't have to worry about change of base because we can put any base, any answer in here that we want. This one is used quite a lot because of the fact that when we're doing our calculations, a lot of what we do now is in base 10. And then finally we have this, ln. And this is the one that we're going to discuss today. We're going to look at it. We're going to see, why is it important to mathematicians? You know, it's got its own button there. We use it quite a lot. It's of huge use in mathematics, in physics. It's around us. It's something that we use. So before I go into the detail of how and what you need for the work that you're going to do in your books, and that particular next exercise, it's actually, we're now going back in that chapter to the second exercise, because we moved on the work of logarithms, because there's some proofs that I want to give to you as I'm going along and I'm talking around this. But why is it important? Why has it got its own number? Why am I stressing to you the importance of E? And that's what I want to look at. And so I'm going to spend a bit of time before we actually think about the work that we're going to do for that particular exercise. I'm just going to spend a little bit of time just developing our understanding, our idea, our appreciation of the beauty of E and the power of it, and why it's so important to us, and what makes it unique, and why we're putting so much emphasis on this particular on this particular number. Why does it have its own button on the calculator? So I'm going to take a little bit of time going back. This is the bit that you just enjoy. Just enjoy the lesson, just enjoy me talking around this, and then at the end we'll pull it all together and I'll show you the key bits that you need for that particular next exercise so you can go on and use it. But before I do that, so remember, exponential functions are functions of this form a to the x, where our argument or the thing that we're looking for is a power or an exponent. And it's intimately related to the work that we've done on logarithms as well, because we will use logarithms as we're going through the work that we're doing today. So let's have a quick think about this number E. This number E, which is basically a constant. You'll see there I've got a 2, this base 2, and there I've got a base 5. Well, E is just a constant, a number, and I'll tell you the size of the number in a minute, but it's just another base, but it's a special base, okay? And I'll explain, or we'll see as we go through our little journey here today, why E is so, why I consider it so special. And to do that, I just want to go back and think about the origins of our number system. I want to have a quick look at how our number system has built up over time. Now obviously this is a big area. I'm just going to put this board thing to the side there. Obviously this is a big area, so I can't cover everything today, and there'll be some things that I'll give you little snippets of, and if you're interested, I mean, why wouldn't you be? It's exciting. Maths is exciting. Maths is beautiful. Absolutely beautiful. It might not have the same beauty inherent in it as you would see in, say, a painting or say music. That's something that has this sort of trapped beauty inside of it that we can all appreciate in some form, but it certainly has this intrinsic beauty inside of it. Every time we're doing these equations, I hate rubbing them off the board because it's like having a Banksy there to me, and I don't want to rub a Banksy off the board. But it has this, I guess to me, it has this intrinsic beauty that doesn't just contain truth and logic, but it's a bit like, unlike a painting or maybe a piece of music, it's like a sculpture to me. It has that intrigue that we need to look into and that interest. So let's go back to, sorry, that was a slight digression there on my own passion of the beauty of everything that we're doing. Let's go back then and have a look at our number system and think about how it's built up. And I'm going to start off with this. I'm going to start off with a very simple equation to solve, and I'm going to write down a linear equation, 2x minus 1 equals 7. And I'm going to solve this equation. We're going to remember, whenever we're solving an equation, we're balancing. So I'm going to deal with the minus 1. I'm going to add 1 to both sides. So we get 2x equals 8. And then I'm going to divide both sides by 2. We're still balancing. Remember, I mean, we all know this now. We all know, we've worked at this, how to balance our equations. Divide both sides by 2. We get x equals 4. X equals 4 is a solution to this linear equation. When we're going to talk about our polynomial equations, and we're talking about solutions to polynomial equations, I'm going to give them the name roots, because often we see the solution to our equations as what we know as the roots of the equation as well. So we get out here a number 4. Now 4 is a number, it's part of a set of numbers that we started with. Let me just draw a quick number line on here. Our number line, so I'm not going to put many numbers on, but it helps us demonstrate this point. So I've got 0, 1, 2, you'd have 3 on this side, you've got -1, -2 in there as well. So I've got my number line here. And you can see 4 is one of these whole numbers that we've got here, and it's part of what we call our natural numbers, our counting numbers. This is where we all start. This idea 1, 2, 3, 4, we can see it back to the origins of mathematics, even as far as people making notches on sticks in a way to count, which is why we call them our counting numbers. So we have this set of numbers, a set of numbers that start with number 1. I'll just write them down at the side. So things like this: 1, 2, 3, 4, 5. Before anything else appeared, our natural numbers were at the centre of everything that we did. So over here, I'm just going to put this in a little set here. I'll draw it with a little circle like this, and we use this special symbol n here to represent our natural numbers. So all these counting numbers that we have fall in here, and the solution to this linear polynomial equation here, this number 4, would lie in here in our natural counting numbers. But let's change it a little bit, and let's say instead of 7 we'll change it to -7. So 2x minus 1 equals -7. Solving this, add 1 to both sides, 2x equals -6. Now we're going to divide both sides by 2, and we get x equals -3. And what we have this time as a root, or as a solution to our polynomial equation, our linear equation, is a negative number, a negative whole number. So clearly at this point, this set of natural counting numbers, these whole numbers 1, 2, 3, 4, 5, and we can keep going to infinity. So this is a large set, you know, it's infinite in size. Our counting numbers will keep going, but actually it's missing numbers now. We've not got the negative numbers in there, and clearly our negative numbers are solutions of polynomial equations like this. You know, we could talk about things like negative numbers when we're thinking about debt and finance, etc. So there is clearly a need to increase our set here, our number system, and that's what we do. If we include the negative numbers, whole numbers here, and our counting numbers, and in fact 0, that's another area you might want to look at yourself. Look at the origins of 0. Go and do some research, put it into Google. There's loads of information about where and the importance of 0. Not just thinking about place value, but a lot of people spend their time looking at these numbers, and there's a lot of really good information out there on Google. So have a look. But anyway, what we clearly need is to increase the numbers that we're using, and then when we increase that, I'm going to put here a z, because what's borne out here is what we know as the integers. Our whole numbers here, including our counting numbers, our negative numbers, and 0. So suddenly, within this set now, because the natural numbers becomes a subset now of our integers. And often you'll see things like this. You'll see z plus and z minus to indicate the set of positive integers and negative integers, etc. So we've got our natural numbers, and we've built up with that with our integers. But there are other numbers. What's in between 0 and 1, 1 and 2, and all of these, if you like, because our counting numbers are infinite in size, and if we look at our integers, well, our negatives will go down to -infinity, so we're now building up a lot of numbers here. And this gets really interesting to me, because imagine in here, what we have halfway between 0 and 1 is a half. It's a fraction. And actually, even though it only looks small, we can fit an infinite number of these fractions just between 0 and 1. And then an infinite number between 1 and 2. And suddenly, this idea of infinity gets bigger. And it gets even bigger. And in fact, if I was solving equations such as this, let's say 3x equals 1, a nice simple linear equation again. Divide both sides by 3, we get x equals 1/3. All these fractions are solutions to certain polynomial equations. And what we have, if you can write a number as a ratio of two integers in simplified form, what we have is what we know as the rationals. The rational numbers, these fractions. And so, and because there's an infinite number, they form part of our number system. So I need to add another set around this. So I have here the rational numbers. We often write these as a sort of cube, like this. But we don't stop there. What about equations such as this? X squared minus 2 equals 0. This is a quadratic polynomial. It's got an x squared in it. Well, solving this, adding 2 to both sides, we get x squared equals 2, and then we take the square root and we get x is the square root of 2. I know we normally put plus minus in there, but let's just take the positive square root for this particular one, and we get x equals root 2. Now, this is a surd. We've all seen that. We discussed it at GCSE. It's a number that has an infinite number of decimal places, and it cannot, there's no pattern to the decimals, so we can't write our surds, our irrational numbers, as a simplified fraction where you've got integer values, a ratio of two integers, so your numerator and denominator are integers. We can't do that with these values, these surds, or our irrational numbers. And I mean, this is where I maybe geek out a little bit and get a little bit excited, guys, but I mean, we're squeezing an infinite number of rationals between, say, 0 and 1 and 1 and 2. And if you think about some sort of numbers like this, if you think about where root 2 would come in, well, root 1 is 1 and root 4 is 2. So between 1 and 2 would be root 2, somewhere it would fit in here. But there's actually infinitely many more than we have our rationals. There's a lot to fit in a number line. So we suddenly have to increase our set here of the numbers we have, and we're going to include, I'll use this P here, we're going to include our irrationals. Now we feel like we're getting there, because all together this set here that we have, that's made up of our subsets of rationals, integers, and the natural counting numbers, and now we've got our irrational, this is what we know as our real numbers. I'm just going to put it here, our real numbers, like this. So the R there represents the set of real numbers that includes all of these. And at one point we would feel that we're done. And we are nearly done. But there is one other area that most of you will work with or get involved with, and that's our complex numbers. It's based around this special symbol here, this I, and I squared is equal to minus 1. Or another way of writing this is I is the square root of negative 1. If these exist, because we always say in the real world we can't take the square root of a negative number. That's because when we're square rooting, we're thinking about what number, when we squared, give us the original number, and when we square a number we always have a positive. So in this, I'm using inverted commas here, but in the real world this doesn't seem to make sense. But in our complex world, in complex analysis and complex numbers, so complex numbers are made up of two parts. The first part it has a real element, and then the other part has an imaginary element, which is what the I stands for. We have a different set of numbers here that forms the last part of our set here. So suddenly our set, if I put the complex numbers in there, see, is complete as we know it. Now, why did I have to sort of talk about this? Why did I want to talk about this? Because ultimately we're talking about exponential functions, functions of the form a to the x. And I wanted to look at, over here, Euler's number. Euler's number. And actually at this point, I'm going to have a very slight digression. Euler's number, or this symbol E, because Euler, although we sort of use the symbol that he had, he's a Swiss mathematician. Other people, Napier was aware of this constant, and when we talk about things like E used in finance, Bernoulli, another mathematician, looked at it when or discovered the value of E when we were looking at compound interest and finance. So we'll talk about that a little bit more later. But I just wanted to mention, there's a slight digression, it looks like Euler, something like that. It's actually the Swiss mathematician Leonhard Euler. We pronounce it oil rather than Yule, so it's Euler. Euler's number. Anyway, why am I talking about all of this when specifically our lesson was meant to be on this exponential functions, and more specifically this value E, this constant E, Euler's number that we know? Well, because this isn't in amongst here, there are other values that we can put into our number system. You can imagine if I extend this number line a little bit here, so I've got 3 and I've got 4, there are certain numbers. So we've talked about what we've got here is our counting numbers, and we've got, if we include the negatives and 0, we've got our integers, and then we've got things like in there you've got a half, so we've got our rationals, our fractions, and then we've got our surds, because in somewhere in between 1 and 2 we've said root 2 lies in there, for example, our irrational numbers in there. But there are other numbers in our set of numbers that we use, which will be somewhere in this bit. One that we use quite a lot is to do with circles, and it's to do with the ratio between the circumference and diameter of a circle. And what we're talking about here is, for example, pi. We use pi quite a lot. So where does pi obviously sits in our number system? We've got it in here, in our set of all our numbers. Pi's obviously in there. We use it. We see it quite a lot. But why does pi, and more specifically E, differ from these other numbers that we've done from here, when we've looked at from here? Well, quite specifically, if I ever solve a polynomial equation like this and get our roots, our solutions out from these equations, there are no polynomial equations like this from which we will get out pi as a solution. There are no polynomial equations like this from which I will get E out as a solution. What we have here is a set of numbers, solutions, roots, that are solutions to our equations, our polynomial equations, and we obtain these numbers using algebraic techniques. And that's why they're called algebraic, I'll write it down here, algebraic numbers. Most of the numbers that we come across in here are algebraic numbers, but pi and E are slightly different. They're rather than being numbers that appear from a set of rules that we've come up with, a set of techniques, algebraic rules that we come up with, rather than coming out in that form, they're more they exist, they're there. If you imagine a circle out there, and we look at the ratio between the diameter of a circle and the circumference, this number pi that we use quite a lot is there. It appears, it's almost there in amongst us without us using our coming up with a set of rules to find these numbers. And so rather than being an algebraic number, it's what we call a transcendental number. So over here, and I'm going to start filling in this board now because it's slightly different, Euler's number E is the base of the natural logarithm. What that means is that here we look at our bases. You've got the base 2, you've got the base 5. Well, e is the base of the natural logarithm, and we write that on the calculator ln. You see it like that. What basically that means, ln just means a log base e. So e is the base of the natural logarithm. That's the first thing. It's on that calculator. You can see it on this. It has its own button. It's on there. It's the base. So when you see ln, then it means log base e. When you see just log on its own, it means log base 10. But you can put any base with that log square button. Here, ln just means log base e. But like pi, e is a, and I write it down here, transcendental number. What that means is, it's not an algebraic number. Algebraic numbers are solutions or roots of our polynomial equations. Pi and e will never be a root of a polynomial equation of this form, ever. Therefore, it's what we know as transcendental numbers. All our numbers are either algebraic numbers or transcendental numbers. So here is examples of algebraic numbers, and pi and e are transcendental numbers. Now this is another slightly interesting fact, at least I find it really, really interesting. But we've talked about infinity just briefly, and I'm not going to go into huge amounts of details, but all of these sets are infinite in size. The natural numbers, we can keep counting, our counting numbers, we can go on forever. So it's infinite in size. And then if we add together the infinite number of negatives and zero, then clearly our integers here are going to be bigger and more, sort of a bigger infinite. Considering infinite goes on forever, then it kind of makes sense that if we've got an infinite number there, then including all these, we get a bigger infinite. So that's what's happening here. And then if we include our rationals and our irrationals and our complex numbers, then our size of infinity is getting bigger and bigger and bigger all the time. But all of these, when we're thinking about things like the natural numbers, the integers, etc., they're what we call countably infinite. Now I'm not going to go into full details of this. If you're interested, have a look at countably infinite. It's a way of, as it suggests, that we can almost count our infinity. And if you look at this on Google, you'll see that there's a relationship. There's a way of sort of listing all our numbers in order 1, 2, 3, 4, 5, so that we can count them in some way, shape or form. But I'm not really going to go into detail on it. But transcendental numbers are what we call uncountably infinite. So we can't count them in any way. In fact, all that actually means is that they're an even bigger infinity than what's going on here already. You know, just imagine it. There are vast numbers of them, and even though there's that many, our studies are only going to really focus on two of them, pi and e. So e, this is like the origins of it. E is a transcendental number like pi. It has these special properties. It doesn't come from our normal our algebraic techniques, our polynomial equations like this. So what is e? Well, it's a constant, it's a number, it's a base like this. Like pi is a number 3.14159, etc. You can keep going on. E has a value as well. And the value of e, I'm going to just put it on here, is 2.718282182845945, and it keeps going. I think I've just given it there to 16 decimal places. Now this is one of these where you can actually rather geekily try and impress your friends, because well, that's not true. I am, I suppose, a bit passionate about what I do. I am a little bit of a geek in that way, but I've not gone away and have this time to learn pi and e to a huge number of places so that I can try and impress my friends who clearly won't be impressed with the fact that I can just remember numbers. But maths is considered, I mean, I've already said to you before that I think maths is intrinsically beautiful. It is, absolutely it is, and the logic it possesses and the power that's in there. When I'm working with equations, it's almost like a ballet going on the board. It's so exciting, and you're solving problems, and in amongst mathematics, and it's a way of looking at it. It's a way of thinking. It's described. My favourite description about mathematics is the science of patterns. It's about looking at it in a different way than a lot of us do. And if we look at this, there's patterns going on. If you look here, let me use a different colour going on here. But we've got, it starts 2.7, but if you can see I've got 1828 and then it repeats 1828. That's quite interesting. Why does it repeat? Considering, like pi, there's no pattern that's going on, but there does seem to be a little bit of a pattern going on. And then here, this 459045 are actually the angles in an isosceles right angle triangle. If you think about it, 45 degrees, 90 degrees, 45 degrees. There's almost like little things that you can spot. I mean, I quite like when we're considering patterns, and one of the things I use, I'm just going to rub this bit out now because we're finished with this just for now. So I'll just remove this bit, allow us to just to show you something else that's quite interesting. And this is one that I use in my classes, an analogy that I use in my classes a little bit. When we're thinking about the science of patterns and how exciting it is to spot patterns in our numbers rather than just accept what they are. Now, imagine this. I often say to the younger members of my classes, what is 11 times 11? So we're talking about year 7s coming now, and they're interested. They're at that age where they want to know more. And so I bring up this problem. What is 11 times 11? And they tell me quite often, because they've learnt a lot in primary school, 121. 11 times 11 is 121. But then I say, or is it? Because it could be 1, 2, 1. Same sort of idea nearly. 121 or 1, 2, 1. The reason I say it as 1, 2, 1 rather than 121, because then I could say, well, what is 111 times 111? And what we get there is not 12,321, which is the actual answer, it is correct. What we get is 1, 2, 3, 2, 1. And suddenly, you can see a pattern appearing. So that the point when we get to, if I put 9 ones in a row, and multiply it by 9 ones in a row, what I get out is 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 7, 6, 5, 4, 3, 2, 1. And I just show it in a different light. If we don't just think about 11 times 11 being 121, but we just, instead, we change our thinking a little bit. And suddenly, what we get out is a pattern that's really beautiful. And to me, I mean, look at the beauty of this. 9 ones in a row times by 9 ones in a row, and if you think about that, what does it mean? What we get out is a number that is a palindrome. It reads the same both ways, but also it runs naturally from 1 to 9 and back down to 1. It's you know, it's quite fascinating. And so in amongst our numbers there may be patterns. Don't ever shy away from looking at these patterns. You know, it is the science of patterns. It's good. But I apologise. That was a slight digression there away from what we were talking about. I just thought that was quite an interesting digression to have. So let's just take a minute to breathe and have a look about what we've been talking about. Just remind ourselves what we've been talking about, and then we'll look back at E and what it is. Right, so we're looking at exponential functions. So functions of the form a to the x, so 2 to the x, 5 to the x. This could be any sort of base. I could put in here, for example, something like this, 7.6 to the x. It's possible to have solutions like this. So it's anything where the power, where the thing that we're looking for, the unknown value, is the exponent or the power. And then we talked about algebraic numbers, so these are solutions of our polynomial equations. And then we've mentioned the idea of transcendental numbers, pi and e being the two that you're going to come across. These are the ones that intrinsically are sort of already in the world in which we're living in, and we find them rather than come up with them using our algebraic techniques. I mean, that's another story all together itself. This idea, does God play dice? Is maths something that exists and we discover it, or is it man-made? What I mean by that is it something that we've come up with a set of rules for? And you could almost argue that this is a set of rules that we're using. So our algebraic numbers comes from something that we've developed, but our transcendental numbers like pi and e are something that just exists around us already and we're discovering them. But that's another argument altogether, so I'm going to stay clear of that one. So, we look at Euler's number. This is the number, well this is used, we use the symbol E. E, this was what Euler used, and it was adopted, this symbol, although other mathematicians were aware of this special constant. It's a transcendental number and it has this value. It's approximately, as we're going to say, 2.718. Like we often say, pi is 3.142. So we're talking about this function, e to the x, where e is approximately equal to 2.718 to the x. That's what we're thinking about when we're thinking about e. So it has that value. So we're going to say, well, why is it important in mathematics? Why do we give so much emphasis to this particular number? Well, as I've put here, Euler's number is special in mathematics, mainly because as the function y equals e to the x, this is what we're looking at, is unique in that its derivative is equal to itself. What that means is, if y is e to the x, that's a function we've got, then dy by dx is also e to the x. We can't ask for anything easier than that. On your exam paper, if you were told to differentiate e to the x, then dy by dx is e to the x. You just write it down again. There's no thought going on there. I mean, we do have to extend a little bit on this, but it's a function that's unique in the fact that when we think about the slope, and dy by dx allows you to think about the slope, and we'll look at this on a graph shortly, but its derivative is equal to itself. Now I want to prove that, but to prove it, I'm just going to go through a proof of our general differentiation of a to the x. That's our starting point. And this is why I wanted to do the work on logs first, because you've got enough to have a general idea of what's going on. And I'm going to go through the proof now. I'm going to just bring in another board here, just have a quick look at the proof and talk you through it, of the differential of a to the x. And then once we've seen that, we'll be able to just show that if I differentiate e to the x, I get out e to the x. So I'm going to look at this just as a little bit of a pre-warning. There is a step in here that you're going to have to just accept. I don't like to just accept something, but the calculus that we're going to do, the differentiation techniques that we're going to do, you're going to look at next year in year 13. So we haven't done it yet, but it's only one step, and I think as long as you can accept that one step, then you know it should be fairly straightforward for you to see, and you don't need this proof is just for me for completeness. So let me just bring this whiteboard in, just make sure we've got enough, just so you can see it slightly differently, and I'm going to go through this proof for you, and then we'll go back and we'll look at the proof that the differential of y equals e to the x is e to the x. So what I'm going to do first, I'm going to prove that the differential of a to the x is a to the x ln a. What that means is, with a number in there, I'll just move it over this side. If my function was 2 to the x, so if y equals 2 to the x, and I wanted to differentiate this, then what I'm saying here, if I differentiate 2 to the x, what I would get out is 2 to the x again, and write it down, but ln 2. So what I'm going to show is that dy by dx of 2 to the x is 2 to the x ln 2. And that's for any base that I put on. If that was y equals 3 to the x, it would be 3 to the x ln 3, and so on. So let's start off. Imagine y is equal to, this is our exponential function, y equals a to the x, our general exponential function. We can put any value for a in there. It's a constant. Then what we can do is we can take logs of both sides. We solved equations like this when we worked on logs, which is why I wanted you to do the work on logs first. So we can take logs of both sides. It's an equation. As long as you do the same to both sides, then our equation is balanced. So we need to just make sure we take logs of the same base on both sides. So what I'm going to do is I'm going to take the natural logarithm on both sides. Now I did say there's one step we need to accept when we're doing this. The reason I took natural logarithms comes down to the differentiation step that we're going to do. So this is another point that will come clearer next year. But I'm just going to at this stage I could take logs of both sides of any base, so I've just chose log base e for this particular one. And the reason why we take logs of both sides when we're solving equations of this form is that now I can use the power rule. I can bring that down in front. So I can write log y equals x ln a. That's the third log rule that we looked at, the power rule, so that x comes down. And I like to say now that x is in play. Rather than being up here where it's stuck up here, I've now got it down, and all I need to do is rearrange this to get x equals, and I can find a solution. So x is in play. At this point, I'm going to differentiate both sides. D by dx, differentiate with respect to x, ln y, and I'm going to differentiate with respect to x, x ln a. Let me just put brackets around these. So I differentiate both sides. So far, I would imagine you could follow this, guys, because we've already done some work on it. So I start off with y equals a to the x. I take logs of both sides so that I can bring x into play, and then I'm just differentiating both sides. All I'm doing here is, remember, I'm keeping the equation in balance. If I differentiate that side, I differentiate that side. As long as I do the same to both sides, then the solutions will be the same. So I'm differentiating both sides. This is a step that you have to you just have to accept until we get to the work next year, and then we'll revisit it and you'll see. But if I differentiate ln y, what I get is 1 over y dy by dx. So we'll talk about that next year, but that's what the differential of that is. On this side, if I differentiate x ln a, what I get out is ln a. That one you could probably understand, because imagine, just as an aside, I differentiate 2x, then it's a number times x. What you get out is just the number 2. If I differentiate 5x, what I get out is 5. We've done work on this already, so that should be fairly clear. Here, ln a for any a is just a number, so what I mean by that is ln 2 is just a number. That's what we said before. You put it in the calculator, it'll tell you what it is. ln 5 is just a number. So what we've got, like 2 times x, is just a number times x, and if I differentiate that, what I get out is the number. And then we're almost there. Multiply both sides by this y, so I get dy by dx on the left hand side. On the right hand side I get y times ln a. But we know up here that y is just a to the x. So finally, if I put that in, dy by dx, instead of y, I'm going to put a to the x, and what we get out is a to the x ln a dy by dx. The differential of our function of the form y equals a to the x is just a to the x ln a. So like I said up here, if y is 2 to the x, dy by dx, I just write down that again, 2 to the x, but I write ln, in this case 2, whatever that number is. So, why does that help me then prove that e to the x, if I differentiate y equals e to the x, what I get out is dy by dx is e to the x? Well, let's just apply that rule there. Remember that I'm going to put it somewhere over here. Remember that if I d by dx differentiate a to the x, what I get out is a to the x times ln a. That's what we've just shown. So let's put that in. If y equals e to the x, then dy by dx, if I differentiate it, well, what I do, e to the x, I write e to the x ln e. So let's write that down. E to the x ln e. But we have to think back now to the previous lessons we did on logarithms. If you do something like this, log 5, what I get out is 1. That's because we're solving equations of this form. 5 to the x equals 5. Well, x must be equal to 1 if the base and the answer are the same. So log 5 is equal to 1. Log 7 equals to 1. Doesn't matter what we've got. Remember that log ln e is just log base e with the answer e. And because we've got an e and an e there, that's just equal to 1. So if I come back to this, e to the x times ln e, well, ln e is equal to 1, so what we get out is just e to the x. So if y equals e to the x, dy by dx is equal to e to the x. So this number, this special number e, has this property that its derivative is equal to itself. That makes it, you know, in itself mathematically, because of that unique property, that makes it a special number in itself. And we can actually see this happen graphically. So I'm going to move over. Now, at this point, sorry, let me just make sure I can get the graphs in here. At this point, this is in your book so you can have a quick look at it. I would like to maybe have a projector at some point so that I can project in using Desmos. Desmos is awesome. You can Google it and it comes up. Desmos is basically beautiful free maths. That's how it has it. Beautiful free math. What more could you want? It is beautiful and it's free. It is awesome. You can use graphs, you can do graphs, etc. But it'd be nice to have some form of projection. But at the moment, I'm doing this by hand, so you have to excuse me. Now, if we look at trying to graph some exponential functions, so I'm going to look at 2 to the x because we've shown here that e is approximately 2.718. So it lies somewhere between 2 to the x and 3 to the x. So let's draw in 2 to the x. I'm going to do this in red. So y equals 2 to the x as a graph would look something like this. That would be y equals 2 to the x. Now, it has a couple of properties on there that we need to just look at. It goes through the point 0,1. All our exponential functions go through that point. And it's asymptotic. It approaches the x-axis, or I'm just going to put in here the line y equals 0. It approaches that, but it'll never touch it. We have looked at this on previous lessons. We also talked about this when we talked about things like exponential growth, because that's hugely relevant with this pandemic that we've got going on at the moment, and this is where the R value comes into it, and people are a little bit worried about keeping that R value under 1, because you can see here with our exponential growth, 1 becomes 2, 2 becomes 4, 4 becomes 8, and very, very quickly on this side, the graph takes off. Over on this side, if we keep it low, it stays low, it's manageable. It approaches, it's asymptotic in this case to the x-axis. What about the derivative then? Well, the derivative, we've already said this, the derivative of 2 to the x is 2 to the x ln 2. So let's have a look at this. And the graph for it would be, I'll keep it in red, but it would be something like this. So I'm going to go through the point 1 here, and it will go something like this. Again, it would be easier if I wasn't just drawing it in on the whiteboard. But this is dy by dx, its derivative, which is 2 to the x ln 2. So you can see there that 2 to the x and its derivative 2 to the x ln 2 are fairly close together. They're fairly close together, but they're certainly not on top of each other. What about 3 to the x? Well, I'll do that in blue. 3 to the x looks something like this. It's a lot steeper. And then it's still asymptotic down here. So I'm going to write that in, y equals 3 to the x. And then we want to look at its derivative. Well, the derivative, this time, instead of being on the right-hand side, is just on the left-hand side. So it still goes down. I'm going to have to try my best here, like this. It still comes down like this, and it's still asymptotic. And there we've got dy by dx equals 3 to the x ln 3. So I've drawn there the graphs of 2 to the x and its derivative, and 3 to the x and its derivative. And a couple of points you need to see is that for 2 to the x, its derivative is slightly further away than 3 to the x, and it's on the right hand side. 3 to the x is here, and its derivative is on the left hand side. So it's almost like, as we go on, if we did 2.1, 2.2 to the x, 2.3 to the x, and plotted its derivative, it will start getting closer and closer. And then it'll go, there will be some point here where there'll be a crossover, and then the derivative goes on the other side. And that crossover is exactly where this number e is. I'm going to use it as a dotted line in here. So it'd be closer, because it's 2.718, so it's closer to 3. So I'm going to just draw it a little bit closer into 3 like this. It's still going to go through the same 0, 1 as all these do. And then it's going to be asymptotic on this side like this. But this point here is the line of y equals 2.718, or e to the x, and lying exactly also on that line, because it's that crossover, dy by dx is e to the x. So graphically, and this is in your books, guys, you can see that, it's a graphical representation of what we've said before, that e is special, that it's the only it's unique in that it's a function whose derivative is equal to itself, as we've proved it algebraically, and now we've shown it graphically. So clearly, it's important. I'm just going to highlight at this point the key learning points that we need as we're going through. So we're looking at Euler's number, not Euler's number, Euler's number. Euler's number e is the base of the natural logarithm. E, we write ln, but that just means log base e, where e is our is a transcendental number that has a value like pi, but its value is 2.71828, and so on. It's approximately 2.718. And it's special in mathematics in that its derivative is equal to itself. So I've got that down there. Now actually, and this is a little bit for your next exercise that you've been working on. So let me just take, well actually I've got some room in here to work on this. So I'll just block this off. So we've said that its derivative is equal to itself. That means that if y equals e to the x, then dy by dx is equal to e to the x. What if it's a slightly different function? So let's say it was e to the 2x. Y equals e to the 2x rather than e to the x. Well, we're going to use this property at this point. It's not just on e to the x, but if y equals e to the ax, then dy by dx equals a e to the ax. So this is another property that we'll look at when we're looking at the different techniques next year to further our journey into to the wonderful and interesting world of calculus and differentiation as well, specifically. But what this is saying is, if there is a number there rather than just x, so in this case it's 2x rather than just x, then we still write e to the 2x, but we just multiply by whatever that number is in front. So in this case, we would get dy by dx, is equal to 2 e to the 2x. So the 2 there, this front of the x just comes down. In effect, you just differentiate this and you get 2 out, and that's what goes in front. And then we could take a function like this, y equals 4 plus e. Well, let's change that from a plus to a minus, because it'll help you guys when you're doing your the second exercise. So y equals 4 minus 2e to the minus a third x. Let's write this in. And we're going to differentiate this, dy by dx. So it's not too difficult, that's why I don't need to spend too long on it. I differentiate term by term. If I differentiate the 4, it just disappears. We've said that you differentiate constants, they disappear. Here, we're going to differentiate this. Well, it's not e to the x, it's minus a third, e to the minus a third x. So that minus third needs to come down and multiply whatever's in front. So what we get out is minus a third times 2, a minus times a minus is a plus, so you get positive 2/3, and then you just rewrite that e to the minus a third x down. So e to the minus a third x still is e to the minus a third x. It's just that there's a number in front of minus a third and a number in front there. So that doesn't disappear. That just comes down in front and joins it, and we get positive 2/3 in front. Right, so we're getting somewhere now. It also has, let me just rub this off. Hopefully you've got that down. You can re-look at the recordings, go back over it, the little sections you need. But this section here, it's almost like, whoa, this section is part of what you need for that particular exercise. So you're going to be looking at different values, you're just going to be putting it in your calculator in the first part of the exercise of e to the, you're going to be looking at e to the x, so you might do e squared, e cubed and stuff like that and find the value of it. And then you just need to know that the derivative of it is equal to itself, and then if your function isn't just x but it's some multiple of x, some linear multiple of x, then you can just differentiate it at this point. So this is like the bit on the video that you might want to pause and just have a quick look at again, just to check you understand it. If you don't understand anything, guys, when I upload this on Teams, and I'm going to put it on YouTube as well, but just send me a message in Teams, and I will go back to it and I'll have a look, and I'll make sure that I help you. There are examples in the book as well that you can have a look at. But there are other interesting properties in that, I mean, this one's just adding to how interesting he is to me, for example. So if I actually drew in a very quick graph here like this, so this is x, and that will write y equals f of x, and our function here is e to the x. So here we're going to write in, that's our function y equals e to the x. It has this interesting property that at any point, so say I draw a line here at the point 2, then the area here, the area is equal to the function value at that point. So what that's saying is, if I put 2 in here, then the function value at that point will be e to the power 2, because it's e to whatever x is, and if x is 2, then the function value is e to 2, e to the power 2, and that is the same as the area under the curve up to that point. It just seems to have these unique properties that are going on. Now there's different ways as well that we can calculate. There's different ways that we can calculate e. So we can use the idea of factorials. So I'll write it down using sigma, but I'll explain what this basically means. One way of calculating e is by looking at the sum of a special series between n equals 0 and infinity of 1 over n factorial. What that means is, we've done factorials. If you do 1 over 0 factorial in your calculator, you've got that exclamation mark button, plus 1 over 1 factorial, plus 1 over 2 factorial, plus 1 over 3 factorial, and then just keep going. What you would get out is this number, e. So, you know, this is a different way of calculating it. Actually, we can go further, and we can look at other areas in which we see e. So let me just move this around and just check that you can see it on there. That looks okay. Actually, there's a little bit of light there, so I'm going to move it round just to make sure you can see it better. Okay, so I've just looked here at a couple of physical problems involving E. We've got things like growth and decay models. You'll see E used quite a lot there. In fact, it kind of makes sense that we talk about growth and decay, population models. So we talked about a little bit about COVID, and we looked at the graph, and it has this growth going on here. And the idea of that is, if you take a family, and that family has 2 children, and then them 2 children grow up, and they have 2 children, and them families get older, and they keep having children like that, then we get this exponential growth going on, where quite rapidly we get a large increase going on. So it makes sense that we see it in our growth and decay models. But this is an interesting one that I talked about the mathematician Bernoulli, who come up with E when he was looking at things like savings models, or more specifically compound interest, or continually compound interest. Because if we take our compound, we should have done, or you will have done this before, when you were studying your GCSEs, and we look at our formula here for calculating compound interest. So it's 1 plus the rate of interest to the power n, where n is the number of years that you're gaining interest for. But it doesn't have to be in years. It can be in it can be in weeks, days. In fact, the quicker you do it, and often when they're doing calculations on interest, it's when we say continue the compounding, you're getting it all the time. And as we increase the number of n, and if we imagine r is 100%, that's a bit generous in terms of interest, then we get actually this 1 plus 1 over n to the n, which for this formula, as it gets bigger and bigger and bigger, then what we get out is E. In effect, graphically, so I'm just going to, you can still see me just on this side. If I do this very, very quickly on a graph, then E, which we said is 2.718, so if you imagine, let me go here, 1, Oh, that's not working there. So I'll do it like this. 1, 2, 3. So E is 2.71828, will be about here. So if I just draw this line, like y equals 1, or y equals 2, or y equals 3, if I just draw here y equals E, which is about this line here, then what happens when we look at this formula, and our formula for continually compounding interest, is that we get this thing going on. Our value will be asymptotic, or it'll approach our value of E. This is where Bernoulli found out about Euler's number and discovered Euler's number. Euler's number, we use the E for exponents because it is to do with exponential functions, so it seems like a natural choice for this particular number. But you can see it approaches it, and as n gets larger, it gives you out this number. So it's in there. The other areas that we've got, things like thermodynamics, relationships between heat and energy, electrodynamics, another area of physics, plane waves. If these are of interest to you, have a look at them on Google. I haven't really got lots of time to go into, but it's seen all the time. And then this bit I do want to mention. Euler's formula, or Euler's identity. I put it both on there because Euler's formula is slightly different than Euler's identity, but often people use them interchangeably and confuse them. But Euler's identity is there is a almost like intimate relationship between E and pi. Believe it or not, pi and E are these transcendental numbers, not our algebraic numbers that we've got in our number system, our set of numbers. Pi and E lies in that set, but they're transcendental numbers, but there's a relationship between them. In fact, it's quite a beautiful relationship in that if I take E, the value of E, and then I raise it to the power pi, but actually more than that, I raise it not just to pi, but to power I pi. It's to do with periodicity of the function, but again, this is something else that we won't be covering, and so this is just for this little bit here is just more for the interest of the topic. But if I take E and I raise it to I pi, and then I add 1, remembering that pi is this number that goes on forever, 3.142, and E is this number 2.718, like pi that goes on forever. I is just our imaginary numbers from our complex system. And then you've got this plus 1, unity. What we get out is 0. We have here what is considered the most beautiful equation in mathematics. They say it's the most beautiful because it's made up of all these really important basic elements. It's made up of E, and it's made up of pi, and it's made up of I, and it's made up of 1, and zeros in there as well. Plus you've got things like this. The plus is in there. You've got raised to a power. So you've got power in there. You've got multiplication in there. You've got I pi. Everything that you're thinking about, all these basic, these really important part of mathematics are in there, in this one equation, showing a relationship between E and pi. In fact, sometimes we write it as this, e to the I pi equals -1. This is what we know as Euler's identity, and it is considered the most beautiful equation that we have in mathematics for that reason. So that's just more of an interest for you. You can see that E is involved in we use E in quite a lot of things. It's important because its derivative is equal to itself. Clearly there's a relationship here between E and pi, and as we go on to do this, you'll see why that relationship exists, because pi is to do with circles, circles is to do with trigonometry, and circular trigonometric ratios, and Euler in his formula showed that there was actually a relationship between E and sine and cos, but that's something again that we'll look at later. And sine and cos obviously is trigonometry. It's all connected in some way. So it's used quite a lot. That's all that board's there for. Now I know we're covering a fair bit, so again at each point I'll just try and remind you of the key points that you need, guys, for this. The only things that you actually need to know is that we're dealing with exponential functions of the form a to the x. E is a special base, e to the x, where e is approximately 2.718, and when I differentiate e I get itself, and then we've looked at different variations of the functions. We've also looked graphically at what's going on, so you can see there where e to the x is and how its derivative will lie on top of itself. And we've looked at these different ways of calculating e, and we've looked at the importance of e and where it lies in our number system. So hopefully we have covered a fair bit there. So just to give you that bit of a flavour, that bit of an understanding as to why it is so important to us, why it's given its own button on the calculator. You know, it is that important to everything that we use, and we're going to be using it quite a lot over the next year as well as we further our journey into advanced mathematics. One final section to close this video on. So I'm going to need a little bit more room on here, but that's to do with sketching graphs. And like we've done before, we've sketched functions and we've sketched their transformations. And we're going to do a similar thing here. We're going to look at, let's just choose something quite nice, nice and easy to work with. But you'll see it's very similar to the sort of stuff you've done before. So I'm just going to freehand put in here y equals f of x and x on my axes. And then we're just going to have a look at sketching. So I'll just write this in here. Sketch y equals 4 plus 2e to the x. You've done transformations of functions. It is part of that second exercise that you need to be looking at. So to do this, we're going to break it down. We're going to start off, if I use different colours, and then black for the last one. So I'll start off, let's see what we're going here, with a red. So let's draw in e to the x. Let's get that in there. So if I did e to the x, it looks something like this. It'd be asymptotic down here, and it'll come up here, and it'll go through one there. So that is, I'll just write it in here, y equals e to the x. We don't want just e to the x, we want 2e to the x. Remember, this is, for whatever value e to the x is, 2e to the x is just double it. It's, as we say, a stretch scale factor 2 in the y direction. So what happens is that distance there will be double to that distance there will be double to that distance. That, if we think about multiplying things by 2, so that distance there is a distance of 1, so we now go through at 2, and then as we go further down here, this distance, you can see it's going to go something like this. So we can draw this in, so it comes down like this. Let's put that in, y equals e to the 2x, not e to the 2x, apologies, y equals 2e to the x. I'm getting a bit carried away there. 2e to the x, because it just doubles it. It's 2 times the function is just a stretch scale factor 2 in the y direction. And then finally, if we add 4 to it, well, what that's happening is every value of 2e to the x now is 4, is moved up by 4 units. So instead of going through at 2, it'll go through up here at 8, something like this, and then it'll still have the same sort of shape, but the main difference is that our 6, apologies. Our main difference is that our asymptote will move up. So instead of being y equals 0, our asymptote moves up by 4 as well. So our asymptote, which if I put in this dotted line here, would now, as that's coming down, be at y equals 4. So our asymptote has moved as well. So again, when you're doing transformations of this, you think about your original function, and then we multiply it by 2, so we do a stretch on that, and then we add 4 to it, which shifts everything up by 4, and that includes moving our asymptote, because it will still be asymptotic, it's just that it won't be asymptotic down here, instead it will be asymptotic further up the axis. Okay? So that should give you enough information now, hopefully, on the importance of E, why it's useful for us as mathematicians, why it has this sort of special status that we give it, like pi, why it is so well thought of, why it's used so much, why it's so important, but also hopefully this video now gives you a bit of a snippet. So the only things you'll need for that second chapter, or second exercise, is an understanding of the differentiation, just the basic bits that I've told you there, and how to differentiate. Look at the examples, and then also thinking about sketching down some transformations. So you should have enough now to have a go at that particular exercise, guys. Feel free to let me know on Teams if you've got any problems whatsoever, but as before, if you take a picture of your work and then upload it onto Teams for me, that would be fabulous. Have a lovely day. I hope you've enjoyed this little journey, and I hope it was worthwhile going back and having a look and think about our number system, so you get a real good idea as to why it's in there, why it's useful. And I will upload the next video very shortly. Again, I'm going to put this on YouTube as well, start sharing around so everyone can watch it. Have a lovely day, guys.